السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah, today we will start. Maybe this is the first actual lecture of the course. Last time we had some definitions. Today, inshallah, we'll start the first actual topic, which is search, and we'll focus on search problems. Before doing that, let me ask you some questions as warming up. First, any one of you did the candy grab problem that we discussed last time? Okay, great. Okay. Oh no, I'm talking. Okay, so you're doing the tutorial and then you will do this. Okay, so you have. I hope that in the weekend you can finish both, inshallah. Inshallah. Okay. Yusuf, do you have a question? Okay, Lord. Okay, so let's now go through some of the questions. What is the difference between general AI and narrow AI? Any answer? Yusuf? Wa alaikum salam. Okay, Yusuf? What do we mean by conscious? Okay, so conscious means aware of everything around the agent in the world. And as you said, general tries to be multitasking and super intelligent in many tasks, not just one. But now, of course, we have specific goal. So that's the main. The agent is good in one task. Thanks, Yusuf. What do you mean by acting rational? Yes, Ghanem, can you raise your hand, please? Not to just open the mic. Okay, go ahead. Yes, I am. Yes, I record the session locally, so it won't appear at your side. Okay, it's not through Collaborate. Okay, now to our question, what do we mean by acting rational? Any answer? What do you mean by rational here, Mustafa? No. Rational doesn't mean humans. Humans sometimes are not rational, right? Okay, so no, it's not acting as humans. Abdurrahman? But in a way, okay, so when we say rational, we mean optimal or the correct way. Okay. Okay. What is the course in one sentence? What is the sentence that can represent the course? We mentioned it last time. It doesn't have to be exact, but what is the meaning of it? Any answer? Any answer? Okay, in a more formal way, we call it, we want to maximize the expected utility. Okay, so the agent in solving a problem or reaching a goal, achieving a task, it tries to do that by maximizing its utility, its benefit, or minimizing the cost, for example, making optimal, trying to achieve optimal solutions. Okay, so the sentence that can summarize the course is just maximize your expected utility. Okay, that will be the goal of the agent always, that we design for the problems. The last question here: what are the key lessons we can learn or we can leverage from the brain? We mentioned 2 lessons last time that we will use a lot in our course in designing agents, AI agents. Abdurrahman? Okay. The what? Okay, so that's the simulation of decisions. Okay, so simulation, that's the one that we will leverage from the brain, that before we make decisions, we try to think about the consequences of the decisions. Okay, and we do that by simulation. And of course, in computers, we do simulation by doing computations also. So computations is one. What is the other? Okay, Ghanem, please don't turn on. Ghanem, please don't turn on the mic without raising your hand. Because if more than one do that at the same time, it will be hard. Okay, go ahead. Ghanem, go ahead. I'm not sure if you mean the memory. So we can make use of the idea of having memory in the brain, which will be the data that we will deal with in the problem, in solving the problem. So the two key components or 2 lessons that we will leverage from the brain are the memory, having memory, which means processing the data that we have, and doing the simulation, which will be done through the computations. Okay, so these are the 2 lessons. Okay, any question before we start our lesson today? Good. So, okay, Saad. Yes. Yes. Mm-hmm. Yes. Did you try to generalize? Wait. That's more complex than I thought. Did you try it? And it always win? Okay, so I think you need more. You need to think about it more in a general way. Okay, I think you can reach maybe a simpler solution that might be optimal. So think about it more. Okay. Okay. You have the weekend to do it. Okay, let's now start our new topic, which is we will cover 2 things, inshallah, I hope: the agents that plan ahead and the search problems. So agents that plan ahead, we have, before we talk about planning agents, we'll talk about what we call reflex agents. So reflex agent consider only what is the world or how the world looks like now, okay, and make an immediate action without thinking about what could happen in the future. Okay, so for example, if I'm driving a car in a lane, and what happens is that one of the cars on my right started to lean towards me. So immediately one solution is that I will move to the left immediately. Okay, so that's a reflection to the state. That's why it's called the reflex agent. Okay, so maybe I didn't look at my mirror to see if there are any cars on the left or not. I would just make a decision to move left. Okay, so this is considering what the world is now without thinking about what could happen in the future. Another example is what we see in this figure, that the agent goal is to reach the apple and just jumps to it without thinking about what could happen if he did that. Okay, because here he might fall. So that's what we call a reflex agent. Okay, so the reflex agent chooses the action based on the current percept or the current state or current memory, and of course will not consider the future consequences of the actions at all. Considers only how the world is now. Now let me ask you a question. Can a reflex agent be rational? And what we mentioned, that rational in the context of search problems, we can consider it finding the solution with the minimum cost. So can a reflex agent be rational? Can it make an optimal decision or an optimal solution? Can find the optimal solution or not? Abdurrahman? Sometimes, very good. Yes, sometimes it, yeah. Yes, yes, yes. So sometimes it can be optimal. Sometimes it can be optimal. Okay, so let's see this example. As I said last time, we will take Pac-Man as a running example in the course. So here we have very simple world. You know that Pac-Man's goal is to eat all the dots. So this is kind of simple world, and the reflex agent here, the strategy of the reflex agent is to move to the nearest dot. Okay, so every step the Pac-Man will move to the nearest dot. Okay, so let me show you what happens if that's the strategy of Pac-Man. Okay, so you saw that it ate all the dots. Was that optimal? Seems yes. I don't think there is a better solution to that. It was not slow. It was it ate all of them in the least with the least cost, with the least time. Okay, so it was optimal in that case. Now, for a more complex situation or more complex world like this, we have dots, but we have walls also. Okay, so let's assume that the Pac-Man again is a reflex agent here, and he will the strategy that he will take is to reach or move towards the nearest dot. Okay, again, that's the same strategy of last time, of the previous slide, but now it's a more complex world. Let's see what will happen. Goes very well now. Then what's going on here? It's stuck. Okay, it is stuck here, and it will stuck forever here. Okay, so let me show it again. So it will start very well, going to the nearest dot, and then stuck. Why does it stuck? Sad? Yes? Yes. Yes, and every time it says right, so it's stuck because it doesn't think ahead about what's the consequence of making this decision. Every time it starts from the state, it forgets everything else, starts from the state, and doesn't consider the future at all. So it takes the same decision, and the same decision, of course, is not going anywhere because there is a wall. Okay, so if it considers what can happen in the future, it would take around here and go to the dot. But because it's a reflex agent going using this strategy, this very simple strategy, it was stuck. So in this case, it won't be optimal at all, of course, and it won't even reach any solution. Okay, so any question about reflex agents? Okay, now let's see what we mean by planning agents. So planning agents is, of course, very different from reflex. It the planning agent considers how the world would be in the future if I made this decision. Okay, so it's doing some simulation or some planning for what could happen in the future before making any decision. Okay, so it asks itself, what if I did that? What will happen? Will I reach something? Will I have a wall? So I will consider multiple paths, multiple sequences of actions before I make an actual action. Okay, so the decisions would be based on consequences of actions and must have a model, of course, of how the world evolves. So because I need to plan, because I will plan ahead, I have to model the world in a way that I know how the world will work if I make this decision. So I have to have a model of how the world actually works. Okay, because I need to know if I made this decision, how the world will change, and then if I made that decision, how the world will change, and so on. Okay, so I have to have the agent, of course. When I say I mean the agent. The agent has to have a model of how the world works. Okay, and of course it has to formulate a goal. It has to know what I want to achieve and test that goal if I reach that goal or not. So let's here define some of the characteristics of planning agents. Of course, there are many different types of planning agents. So an optimal planning means a planning that will reach the optimal solution. And again, the optimal solution here is the solution with the minimum cost. Of course, that depends. The cost will depend on the problem. Okay, so that's what we mean by optimal planning, is to find the solution that is the optimal solution. Complete planning means that if there is any solution, the agent will reach a solution. So that's what we mean by complete planning. So optimal planning is to find the best solution, the optimal solution, the minimum cost solution. Complete planning is to find a solution. That solution might not be the optimal, but if my planning is complete, it's guaranteed that I will reach a solution if there is one. Okay, the difference is clear. I hope it's clear. Any question about that? Okay. Now we will see in an example what is also the difference between planning and replanning. So let's start with what we call a Mastermind Pac-Man, which is a planning agent. So here Pac-Man will plan ahead for an optimal solution, for a complete not a complete because we are say complete, but for a full solution. Okay, to the end, until from the start state here to the end, to reaching the goal. And the goal, of course, usually in Pac-Man games is to eat all the dots. Okay, so you will see here now that Pac-Man, before making any decision, before making any action, it will plan ahead for the entire solution and then execute that plan. Okay, so let's run this and see what will happen. You will see here that some indications that the agent is planning now and considering multiple solutions or multiple paths. Okay, of course we will understand the details later, but let's think now that planning means that I'm trying or simulating multiple solutions, okay, with sequences of actions, or considering multiple ways of solving the problem. And of course, as the problem is getting more complex, I will have more and more possible ways of reaching the goal, and I need to consider all of them for a planning or mastermind action or planning agent before I make any single action. So let's see how this will work. So we'll see here that it is pre-calculating some of the paths, and then you will see so still now planning now it had 1,000 paths or 1,000 possible solutions. It considered 1,000 solutions, 2,000 solutions, and still it didn't make any action yet. Okay, and once it finds the optimal solution, now it found the optimal solution, it executes it right away. Okay, and you'll see that it is the optimal solution, which means that it is the solution with the minimum cost. Okay, now let me ask you a question. Let's do it again quickly. I will just move forward for the planning time and show you how it will execute that plan. Now let me ask you, what is bad about this agent? What is bad about this agent? Yusuf? Yes, it takes a lot of time in the beginning, okay, because it has to plan ahead for the entire solution. Okay, so it's very slow in the beginning, especially, of course, as you said, if the problem is more complex, it will take even much more time. So that's the problem with planning agents or with Mastermind agent. Now let's think about replanning. Let's talk about replanning. So replanning agent here, it doesn't plan ahead for the entire solution. It formulates a plan. It formulates a goal with every step, and the goal here is to reach or to eat the nearest dot. Okay, so in every step, it formulates a new goal, okay, which is eating the nearest dot, and executes it. So so in the beginning, let's say that we are here. Okay, so this is the nearest dot. So it considers all the plans that will achieve that goal, which is eating this dot only. It finds the optimal plan for that, or optimal solution for this problem. It executes it, and then replan again for the next goal. Execute it, and then replan again for the third goal. Execute it, and so on until it reaches the goal of the entire problem, of the original problem. Okay, so it replans with every action, with every step. It doesn't do planning for the whole solution in the beginning. It's like dividing the problem into very small problems and plan for each one at a time. Okay, so it plans for the first one, execute the plan, plans for the second one, execute the plan, and so on. And in every step, it changes the goal, the local or the temporal goal that it has, the local goal that it has, not the global goal. The global goal is to eat all the dots, of course, but it formulates a goal, a temporal goal, or temporary goal with every step. Let's see how this agent will act, and then we'll take your questions. So you will see that it starts right away, okay, and it might not be optimal, of course. It might not be optimal, but it didn't. It was not as slow as the planning agent, as the Mastermind agent that has to plan for the entire solution before it starts. This one again, I will execute it again. Okay, so it starts right away because it plans for a very small goal every time and execute that plan. Okay, so that's what we mean by replanning. Questions? Raise your hand, please. I will not be able to read all of your text messages. Raise your hand, please, if you have any question. Hamza? Yes. It depends on the strategy. It depends on the search strategy. Okay? Sometimes we have to break the ties, of course. Okay, so we didn't discuss yet the search strategies, but if there are multiple solutions that are all of the same cost, then you can break the ties, of course, arbitrarily. Yes. Okay. You're welcome. Any other questions? Okay, so let's move on. Now we discussed different types of agents. Now we'll talk about specifically about search problems. And what do we mean by a search problem? So a search problem consists of 4 things. Okay, so if we manage it to convert a problem in the real world into these 4 things, we call this problem a search problem. So what are these 4 things? The first one is what we call a state space. State space. This is a space of all possible states of the world that we are modeling, that the agent is acting in. All the possible states. So for example, in Pac-Man, it will be the position, the state, any state will be the position of Pac-Man and the position and the position of the dots and whether they are eaten or not, for example. Okay, so listing all the states, the possible states in that world is the state space. Of course, we can just describe it. We don't have to list them all, but the space has all of these possible states. Okay, and the state is just what we mean by state here is how the world looks like at any time. What are all possible ways of the world in the problem that we are solving? Okay, and we see, of course, we will see examples very soon. So that's what we mean by a state space. So that's the first component. The second component is what we call a successor function. So the successor function tells us what are the possible, or tells the agent what are the possible actions that he can make next. Okay, so the input to the successor function is the current state of the world, and the output is all possible actions. Every action has its own cost and the next state that this action will lead to. So for example, let's say that I am in that state now. The agent is in this state now. The agent is here, and these are the dots. Now the agent has 2 possible actions. It's either going east with a cost of 1, because it will be just 1 move, or going north with also cost of 1. If we go east, then this will be the new state. Okay, because it will eat that dot. Okay, so the dot is not there, or it will eat the dot in the north, and that will be the new state. So again, the successor function will take one state, which is this state in this case, and provides a list of actions. Each action has a cost and has a next state. Okay, so basically this function will help the agent reason about the possible actions and the possible solutions, because now I can simulate. If I have this function, then I can simulate multiple actions and see what will be the cost of these actions, multiple sequences of actions. Okay, as we will see inshallah later in the course. So that's the successor function. That's the second component. The third and fourth component are the start state and the goal test, or the goal state. So the start state is where we start solving the problem. The state of the world when we started to solve the problem, and the goal state, of course, that's the state that we want to reach. Okay, and this is associated with what we call a goal test, a test that will tell us whether we reached the goal or not. Okay, if we formulate any real problem into these 4 things, then this is now a search problem. The beauty of this formulation, or this what we call interface, if we have a generic search strategy, a generic search algorithm that will solve any problem that has been represented this way, then we can solve any real world problem that can be converted into this interface. So if I have a real problem converted into this search problem, okay, using these 4 things, if I manage to have these 4 things for this real problem, then any algorithm that I have to search to solve the search problem can solve the real problem, because I modeled it into a search problem. And the solution in this case will be a sequence of actions. We call it also a plan. So sometimes we call the solution a plan, okay, or a solution, same thing. It's a sequence of actions. Okay, so the plan is a sequence of actions, but the solution is the sequence of actions which transforms the start state to a goal state. So there are two things here. The plan is a sequence of actions. Okay, that plan, if it takes the agent from the start state to the goal state, then this is called a solution. This is called a solution. Okay, now let me stop because this is very important to make sure that you understand it and take your questions if any. Any questions about what we mean by a search problem? So a search problem has to have these four things: the state space, successor function, the start state, and the goal test. Any questions, Abdurrahman? Yes. It can be applied to any state. Yeah, it has to be. Yes. Yes, it is general. Yes, it is one function that can take any state and provides the possible actions on that state. Okay. Any other questions? It's very, very, very important for you to understand this because we will base maybe the first half of the course on this formulation. Fact? Turn on your mic, please, Fahd. Fahd? Okay. Any other questions? Okay, raise your hand, please, if you have any question. Okay. Then let's move on. Okay, here I want to say that, as I said earlier, the search problems are just models. Okay, so we have a real problem, a real world problem, and we model it as a search problem. Type. What does that mean? That means that some of the details in the real problem will not be considered in the search problem. It's just a model. Model means it's just a representation of the problem. It might not capture all the details. And that, of course, depends on the problem that we are solving. Maybe the problem that we are solving doesn't need to know some details. Okay? Okay, now let's take an example of a real-world problem, and we'll try to convert it into a search problem. The problem here is to go from a specific city in Romania. We are traveling in Romania. We want to go from a specific city called Arad to another city called Bucharest, which is the capital. Okay, and I want to find a solution for that problem. Can we convert it into a search problem? Let's see. The search problem has four components, as we said. The first one is the state space. Okay, and of course we are given that map that shows us the cities and the distances between each city. What are the states here? What is the state space? What are the possible states here? Ghanem? Arad, yes. Tell me generally, describe the states generally. You don't have to name the cities. Okay, Ghanem, we are talking about we're talking about the state space now. Okay, we are not talking about the other components, just the state space. What are the states in this problem? Okay, so I got the idea that you are trying to do. Okay, so let me comment. Let me comment on that. You don't need the numbers, you don't need the names of the cities. So don't consider only the start state when you describe the state space. So the state space should have all possible states. and the possible states here are just the cities that we will visit. Okay, so the names of all cities are the possible states, because I can be, as an agent, I can be, or as a person, I can be in any one state at any time. Okay, so I will assume that I will model the problem as this way, that I will go from one city to another in trying to reach my goal, going from Arad, or Arad as you pronounce it, to Bucharest. You can visit some cities, so I can model the state space here by the cities that I visit. Okay, so every state will be just one city that I'm visiting right now. Okay, yes. No, that's the successor function. Yes, not step. Okay, that's a good question, Ghanem. The state space is not the steps. The state space is the states, the possible states of the world. Okay, in Pac-Man, where the Pac-Man is and what are the current dots, for example, that's the state of the world. Now, the space of the states is all the states that are possible in the world. Okay, Abdurrahman, do you have a question? We'll talk about, okay, يعني not to switch from this example. We'll talk about Pac-Man next. Okay, so let's focus on this example now. Yes, yes. Actually, it's the opposite. The states are the cities. Okay, every city is a state. Yes. Okay. Okay, so the state space is the cities. Now, what about the successor function? We said that we have to have four things, right? The state space, successor function, start state, and the goal test. So what is the successor function now? Anyone else other than Ghanem and Abdurrahman? I can name someone else, by the way. How about Saeed? Saeed, are you with us? Yes. So what could be a successor function here? Any idea? Any guess? What is the definition? What should be a successor function? What does it do? So a successor function. Any idea, Saeed? Okay. How about Mubarak? Mubarak? Mubarak, are you with us? Okay, Faisal? Faisal? I don't hear you, Faisal. Okay, try please to solve your problem with the mic. We cannot move on this way. Okay, Yusuf? No, Faisal, it's not working. Yusuf? Wa alaikum salam. No, generally. Describe it generally, Yusuf. Not very good. So it takes a state, which is what here? No, that's the start state, but generally it's a city, any city. Yeah, so the successor function is general. It doesn't work only on the start state. Okay, so the successor function takes a state and provides us with the list of possible actions. So the state here is the city. Okay, and what are the actions? Generally, not you are again focusing on the start state. Generally. Very good. So the actions are going to the neighboring cities through the roads. So for example, if I am in this if I am in this city, in CBU city, for example, I can go to this, I can go to that, to this, to that. Okay, so we have 4 roads possible that I can take. And what is the cost associated with every action, Faisal? Yusuf? Yes, it can be here the distance of the road between the 2 cities. And the next state, of course, will be the next city. Okay, now what is the start state? This one is easy, right? It will be Arad or Arad. That will be the start state. And the goal test, what will be the goal test here? Any idea? Ghanem? Bucharest. That's the test. What is the test? So Bucharest is the goal state. But what is the goal test? That's not the goal. No. That's the goal test is simpler than that, Ghanem. No. Okay. So Muhammad Ahmed, what is the goal test? Thanks, Ghanem. Where is the test here? Okay, so the goal test is the test that I will implement, or I will check to see if I reached the goal state or not, if I completed my goal or not. So what is that goal test here? No, why? Why is that there? So I want to reach Bucharest, right? No, but I want to reach Bucharest, right? I want to reach Bucharest. That's the goal. So the test is just to see whether my state is Bucharest or not, right? That's simple. Because if the state I am in now is Bucharest, then I'm done. Regardless of how I went there. How I went there is the solution. Okay? And the solution might be optimal or not. I have many solutions here. Right? But the goal test is to test whether I am in Bucharest or not. Okay? Now, again, Muhammad, you were with me, right? Who was talking? Yeah. So what is the solution in this case? I mean, what could be a solution? Not the optimal solution, but what could be the solution? How can I represent a solution? No, how can I represent a solution here? Okay, that's what I want to reach, but if I have a solution, how can I represent it? And how can I say that this is how I can solve the problem? Yes, very good. So a path from the start state to the goal state. So in this case, that's generally. But in this specific problem, it will be the cities that I will visit until I reach Bucharest, from Arad to Bucharest. Okay, or the roads that I will take from Arad to Bucharest. Okay, so that will be the solution. Of course, in this case, we have many solutions, right? I can go this way, or I can go this way. There are so many solutions. Some of them might be optimal, some of them might not be optimal. But any solution will be a sequence of actions, right? And the actions here is taking roads, so it will be a sequence of roads, taking the agent from Arad to Bucharest. Any question about this example? No questions? Okay, now, as I said, the world state can include many details that we might not need. Okay, so to show you an example, we have 2 examples on that slide. Okay, the 2 example problems. So the first problem, we will start both problems from this world. So let's say that this is the world that we are acting in, the Pac-Man world. But up to this point, I didn't state what the problem is. Okay, so now the first problem that I want you to think about is what we call pathing. Okay, pathing problem in this world. So what's pathing? Pathing means the Pac-Man wants to go from this starting state to a specific location. So let's say that this location, for example. Okay, so I want to take the agent, or I want the agent to go from the start position to this position. That's or a specific position. That's pathing. Okay, that's the real problem. This is a problem in the real world. Now let's think about how we formulated as a search problem, and more specifically, what are the states here? Okay, we will only here focus on the state space. Do we have to capture every detail in the environment, in the world, when we model it as a search problem or not? We will see that it really depends on the problem itself. So for this specific problem, what will be the states? Hamza? Yes, so the state is the position of Pac-Man. Okay, type. What else we can have? Anything else we need? So who is talking? Ghanem. Okay, again, Ghanem, please raise your hand, please, before you answer, because there are others before you. Saad? Saad? Okay, so Hamza said that in the state now, we can have the location of Pac-Man. Okay, it's needed, of course, because we need to go from one location to another. I'm asking whether we need anything else to represent in the state. Yeah, for example, how about the what do you mean by states? Well, we don't need anything else. You don't think we need the dots, the location of the dots? Why? Why not? Yes, very good. Yeah, so we don't care about where the dots are and whether they are eaten or not. In this specific problem, in pathing problem, we don't care about it. So the states will be just the location. The state will be just the location. Okay. Of course, the successor function will take the location and update it based on the action that I will take. And the goal test will be whether the location, the current location, is the end location or not. That's the goal test. If I am in the end location, then I'm done. I reached the goal. Okay, so that's the pathing problem. Now, if we change the problem to be the regular Pac-Man problem, which is eat all the dots, what will be the state in this case? Ghanem? You mean the positions of Pac-Man and the dots? Okay. Okay, so we understand, of course, the location of Pac-Man. How about the dots? Do we need the location of the dots or something else about the dots? You need the dots, but what exactly about the dots? Just the location? Yes, very good. Okay, very good. So for every dot, we need to know whether it's eaten or not. So it's like a Boolean value for each dot, right? That's what we need. So we need the location, the position of Pac-Man in the state. We need the position of Pac-Man, and also the positions of the dots, and for each dot, whether it is eaten or not. So it's like a Boolean matrix of Boolean values. For each dot, it has a Boolean value, whether it's 0 or 1, whether it's eaten or not. Okay, so the states will be xy, which is the position of the Pac-Man, and the dot booleans, one boolean for each dot. And the successor will take one state and update the location, and possibly a dot boolean if I went over If the agent went over a dot, then it will be eaten, which means that we'll have to update also the state of the dots. So the location will be updated, and the dot boolean can be updated. And the goal test, of course, is to test whether all dots will be false. Okay, we didn't say here dots are eaten because there is no eating in the state. It's just a model. So the model here is a boolean value for each dot. So the goal test is to find out whether all dots are false or not, because false here means it is eaten. Okay. Any questions so far? Because we'll have to stop here. Any questions about the search problem? So now, if you want to convert any real problem into a search problem, you will have to think about these four things: the state space, the successor function, the start state, and the goal test. Muhammad? Okay, I will try inshallah to do that. Not guaranteed, because sometimes I what do you mean by still? This lecture, of course, yes, because I didn't upload it. The previous ones are there. Usually I make some changes before the class, but I will try to put the slides inshallah before the class. Any other questions? Okay, so then we'll stop here. Inshallah, we'll talk to you on Sunday. Assalamu alaikum wa rahmatullahi wa barakatuh.